Okay, let's start. Good morning. So this week we have our second midterm. So when it comes to topics about integral calculus on the syllabus, I mention these elementary functions, these sort of nice functions that you know from calculus, and there's a study of them, of course, from a more rigorous point of view, like what is the exponential function, what is the logarithm function, and so on. But I think I'm going to excise that part. Maybe we can get back to it later when we start talking about power series and stuff. But I think today I'd like to discuss some further sort of consequences of the fundamental theorems in the form of two specific examples about calculations, and then two important formulas. One of them is the U substitution formula, at least one version of it, and the other one is the integration by parts. And then tomorrow, if time permits, we're going to discuss improper integrals, where the domain of your integration is unbounded, possibly. In applications, this is very important because engineers and other people would like to be able to make sense of things like 0 to infinity sine of x e to the minus sx dx. S is something called the frequency parameter. And so they would like to be able to imagine this as a function of s, and this does make sense. It turns out it is infinitely differentiable in s. It turns out there's a bunch of different things. So at the very least, I would like to be able to discuss what this could mean. Of course, it's going to turn out that this is just a limit as lambda or rho goes to infinity. This guy. This is what is called the Laplace transform, by the way. Turns out to be very important. So tomorrow, if time permits, I'd like to discuss this business a little bit, integration over unbounded domains. But today, I would like to focus on the fundamental theorem of calculus. So I'm going to be taking attendance today. Okay, so let's look at this example. It looks bizarre, but let's try to parse this. Forget about the d by dx for now. I have the endpoints, some x arbitrary value. From x to 2x, I'm integrating this guy. Okay. Now, this looks like an abstract math thing that should not be applicable, but in reality, I can try to come up with a physical situation where this is useful to be able to integrate. For instance, if I were to assume that x is positive, then I can imagine that, so say x is positive, then I have this rod. Its endpoints are variable in time, perhaps. As x varies, the endpoints vary because perhaps it sort of expands and contracts. And for whatever reason, you decided to model the contraction and expansion of the endpoints by x and 2x. And you know for some reason that the density of this rod is sine of t squared. It's a bizarre material somehow. And you're trying to compute the mass of it. Okay? And so this mass of this rod with this density would be precisely this integral. And then you're trying to see how this mass changes in time. Okay? Now, probably if you're physically inclined, probably the mass shouldn't change or something like that, but this is sort of like a simple interpretation. Okay. So this is sort of some intuition as to why one would like to be able to make sense of this. But from a rigorous point of view, does this make sense? Any ideas?
Yeah, the integral expression is just a function of x. So, I mean, I can't guarantee it's differentiable. I would assume it's differentiable considering we've written it down like this.
Yeah, we're going to get to that, exactly. Of course, in this class, just because someone is asking you to compute the derivative of something doesn't mean that it is differentiable, right?
Yeah.
Included in this question mark is also the statement that this is differentiable. First, you need to show that this is differentiable and then differentiate it. Okay, because we never believe anything in this class unless we can prove it. Okay, so let's think about this. For any x, I would like to spend some time on this example because when you first start dealing with these kind of things, it looks very bizarre. X to 2x, let's say that x is positive for simplicity. If x were negative, I probably would need to interpret this as a signed integral. Unsigned integrals are more pleasant as far as I'm concerned. So let's just focus the x positive case. Then x to 2x is a closed and bounded interval. Okay. Certainly, sine of t squared is the composition of two continuous functions. Hence, itself is continuous on this interval. Hence, by one of the things that we showed, it is Riemann integrable. Okay. So t goes to, maybe I should write it like this. T goes to t squared, which goes to sine of t squared. It's this composition function, is continuous, hence integrable on I. Let me just write it like this. Is C0, which is a subset of R. It is Riemann integrable. Hence, this is a well-defined expression. Well-defined function. Okay. So now I'd like to start using the fundamental theorems of calculus that we discussed. And so using this cocycle thing that we had discussed, I can write this integral, as a certain function more explicitly. And so recall that we had this. For any gamma, this function is integrable on I, but in fact, it is integrable on any closed and bounded interval. For any gamma positive, or non-negative I could have done also, I can define this function. Okay? Now, this function, the function that I'm integrating, is continuous to say the least, which means that by the fundamental theorem of calculus, this guy is differentiable, and its derivative is the integrand. And in fact, what I can say is the following. By fundamental theorem of calculus, since the integrand is C infinity, is C infinity, infinitely many differentiable, this function that you define always is better. It has more derivatives relative to the thing that you're integrating. In this case, if you have infinitely many derivatives, f sub gamma 2 is going to have infinitely many derivatives. And let me say, and f sub gamma is an antiderivative of this lowercase f. Maybe I should have called it something. Let me call it lowercase f. So f of t equals sine of t squared. Technically, according to our conventions, this is the second fundamental theorem of calculus that I used. But then, once I have an antiderivative of an integrable function, the first fundamental theorem tells me something, right? Then, again by FTC1, maybe I should put here FTC2, for any alpha and beta on whatever domain, this guy is equal to this. Okay. Well, if I were to choose alpha to be x and beta to be 2x, then I would have a nice expression for this thing that I'm trying to differentiate. Now this becomes, for any value gamma, I can write it like this. Okay, but then we also had this co-cycle property for this family of functions. Let me remind you that as well. Because basically I want to get rid of this, or maybe I don't need to get rid of it. I guess this is fine. Because if you want, this I can think of as f sub x of 2x. So this thing that I'm trying to differentiate, is f sub x of 2x, which I can write as f sub gamma of 2x minus f sub gamma of x. If I wanted, I could have chosen gamma to be 0, for instance, but it's not going to matter. Okay. But then that means, let me continue from here. That means that this expression that I'm trying to differentiate, this guy, is this, which is equal to this. Now this is a differentiable function of x. This too is a differentiable function of x. And so is their difference, because differentiability of the linear combinations are preserved. And I have this nice formula. So d by dx of x to 2x sine of t squared dt is the derivative of this expression. F sub gamma of 2x minus f sub gamma of x. I can distribute this derivative, and then I have this. So prime. And then this becomes, so you see, capital F is an antiderivative of lowercase f, which means that when I differentiate, this is just going to turn into lowercase f. And so ultimately, this ends up becoming sine of 4x squared minus sine of x squared. And so I was able to show that this thing that I am hoping to differentiate is differentiable, and furthermore, its derivative has to be that function over there. Any questions about this? Except that you're going to make a mistake like this. That's why I did this. You see, you have to be careful. You have to apply the chain rule here. This is capital F composed with multiplication by 2. So the derivative of the guy on the outside, evaluated on the function, times the derivative of the thing inside. There's a factor of 2 here. Okay? Be careful about these kind of things. Any questions about this? So I have this expression, and I try to reduce it to expressions that I have seen in the fundamental theorems. I should also mention, I've been looking into different textbooks and stuff, why this is the first fundamental theorem is called the first fundamental theorem, and the second one is called the second fundamental theorem. But from book to book, it changes actually. For some books, it's the second, and for some books, it's the first, so it actually doesn't matter that much. Okay? Any questions about this? Okay, let's do another example. So this was in the textbook, by the way, and this is also from the textbook. I'm going to fast forward this time this procedure of making sense, but in general, when you sort of encounter expressions like this, I think it's a good idea to sort of think about it step by step and at least heuristically realize that it should make sense. And if it doesn't make sense, you shouldn't try to compute it, of course. Did you all sign the sheet? Oh, there you go. Okay, so here's another example. This is perhaps even easier. E to the minus t squared dt equals what? Okay. Same idea, right? So the thing I'm trying to integrate is infinitely differentiable. And so if I were to think about f sub 0 of, let's say, y, the function from 0 to, given by the integral from 0 to y, e to the minus t squared dt, then f sub 0 is going to be c infinity, infinitely differentiable by the fundamental theorem. And this guy is nothing but the composition of f sub 0 with the sine function. By the chain rule, this is equal to this. But uppercase F prime is the integrand. So this is e to the minus sine of x squared, not the composition of sine with itself, but sine of x times sine of x as numbers times cosine of x. That's how this works. Again, I'm not forgetting differentiating the thing on the inside. Chain rule requires this. We talked about how this chain rule too sort of leads to a different type of cocycle. From a computational point of view, of course, it's also important to not forget the factors, but from a fundamental point also it is important. Questions? Now, I'm still thinking about whether or not I should include problems like this in the next problem set, because it's kind of hard to sort of ask properly this computation. I don't like asking things like evaluate this, because you can just say, technically speaking, this guy is equal to itself. Or you can say, you can sort of write it in a different way that doesn't necessarily equal to this. But I can say perhaps, write this expression as a linear combination of compositions of exponentials, trig functions, and polynomials. That could be sort of one way of asking this. So maybe I should write that. So I would say perhaps this is well defined, and it can be written as a finite linear combination of compositions of exponentials, trig functions, and polynomials. And can be written as a finite linear combo of compositions of exp, log, trigs, and polys. Now this is a failed state. Either you're able to express it. Of course, if it cannot be expressed, then it becomes hard. It becomes hard to figure out that a certain integral cannot be written in terms of these elementary functions. And there's a theorem, in fact, that tells you when you can do that and so on. But we're not going to get to that. So this is this. Now I would like to switch over to the more abstract applications of the fundamental theorem, or theorems, I should say. Let's first start with integration by parts, and then switch over to the U substitution. Okay. Before, though, we're going to use a certain idea that I'm going to leave to you as an exercise. So far, we talked about how, for instance, that was also an exercise, but still, how the sum of two integrable functions is integrable, and a scalar multiple of an integrable function is also integrable. And you have certain equations and so on. It turns out that it is also the case that the product of integrable functions is integrable. Okay? And so I'm going to leave it to you as an exercise. Let's say I have a closed and bounded interval, as usual. Lambda to rho, it is closed and bounded. If two functions f and g are Riemann integrable on I, then so is f times g. Okay? So you can multiply two integrable functions to get an integrable function. Now, if you were to switch your theory of integration to something like Lebesgue integration, this is not necessarily true in general, for instance. But in Riemann integration, it's fine. And of course, the integral of the product is the product of the integrals. This is also false. This doesn't work. That's why you have integration by parts. Integration doesn't work well with multiplication. The next best thing is the integration by parts. Okay? So substitute integration by parts. And you can think about it in this way as well. Integrals should be pretty much sort of the inverse operations of differentiation. The derivative of the product is not the product of the derivatives. Okay, it's again complicated. Just like you have a product rule for derivatives, you have a product rule, so to speak, for integration. And the product rule for integration is integration by parts. Or Leibniz rule, if you want. Rule for integration. Maybe I should say a couple of words about how to prove this. Instead of showing for arbitrary two functions f and g, f times g is integrable, it turns out it is better to show, or it's easier perhaps, to show that f squared for one function is integrable first. That is also not true in general for more complicated integration theories. So, first show, so step 1, if f is integrable, then so is f squared. And then step 2 is to realize that you can write f times g in terms of other functions that you know by now are integrable. Namely that f plus g squared is f squared plus 2f g plus g squared, which means that I can solve for f times g as fg equals 1 over 2 times f plus g squared minus f squared minus g squared. This is one instance of what is called a polarization identity. And so if you know, assume that you did step 1, if you know f and g are integrable, then certainly f plus g is also integrable by the linearity property. By step 1, this square is integrable, so is this square, so is this square. This is a linear combination of integrable functions, which means that f times g has to be integrable also. That's one way of showing this. Another way of showing it is to go all in, right? Sometimes if you're trying to prove something, it's easier to prove something stronger. If f is integrable, and let's say I have a function psi from, let's say it is continuous from the image of f to R, so that I can compose f and psi, then psi composition f is also Riemann integrable. And then if you have this, you can apply this expression to step 1, where psi is the square function. This also, for instance, shows that if f is integrable, so is its absolute value, if you were to choose psi to be the absolute value function. This is slightly trickier. I was thinking of doing this in class, but I'm not going to do it. And maybe I want to say something about one way of proving this, okay? And because this proof method is very useful. So you're going to have to open up the definitions of integrability and so on. And you're going to have to deal with partitions, ultimately. Your idea, or the standard idea for these kind of things, is the following. You take a partition. It's an arbitrary partition. It is a bunch of pixels. Now you split your pixels into 2 categories. One category is the pixels where whatever function you're trying to handle behaves badly, and the other part is where the function behaves nice. So, idea, given any partition and epsilon, decompose P into 2 disjoint subsets. It's going to be a vague statement, what I'm saying here, but it shows up everywhere. P, let's say, epsilon, comma bad, union P, epsilon, comma good. So epsilon is your error margin, and you're separating your pixels into 2 categories, where a pixel is in this bad category if whatever you're trying to control behaves worse than epsilon, and otherwise if it behaves better than epsilon. Worse than epsilon behavior And here is the set of pixels where behavior is better than epsilon behavior. Whatever this means. But it means for behavior to be worse than epsilon or better than epsilon depends on the context. And that's where sort of the complications start happening. But in this exercise, it's going to be useful. So you're going to take a partition, perhaps, for the integrability of this composition. And then you're going to say either the gap for a given pixel relative to this composition function is beyond epsilon, in a sense, or it is less than epsilon. And then you're going to separate it into two pieces, like in this case. And then you're going to handle this part, and then you're going to handle this part to get the bound for the difference between the upper and the lower Darboux sums. Okay, this is like a philosophical statement almost, but this idea shows up everywhere. Somehow, the idea should be that this part should have base small length. So this part should add up to something like this. Its base is very small, but maybe its height is high. And this has base very large, but its height is very small. So this is the bad part. This is the epsilon bad part, and this is the epsilon good part, essentially. Okay. This is like a philosophical statement. Okay, I'm going to leave that to you, and I'm going to assume this. And so assuming this, integration by parts says the following. Let me ask before, are there any questions about any of this? This is, of course, like a rather optimistic perspective. You want something to happen, and you basically say, okay, maybe it doesn't happen all the time. With some sort of low probability, it doesn't happen, but that low probability is so low that I can basically ignore that happening, right? That's sort of the idea. Now, how come that optimistic perspective works in math is a different matter, of course. That's a philosophical question. Okay, integration by parts. How many of you have seen something like this before? Okay, good. So how do you do this? Maybe let's remind ourselves a little bit. I like to use the letters U and V. Right, so U dV is UV minus V du. It should be something like this. Okay. Now, formally, it's going to be a little bit more complicated, of course. You have to be careful about the assumptions and so on. Let me let two differentiable functions whose derivatives are integrable. Be differentiable. And f prime g prime be Riemann integrable. In particular, they have to be bounded, of course, because any Riemann integrable function in particular has to be bounded. We didn't define the Riemann integrability for unbounded functions yet. Okay. Then for any alpha and beta, this is going to be a statement for signed integrals. this is equal to f of beta g of beta minus f of alpha times g of alpha minus alpha to beta f prime of t gt and dt. That's the integration by parts formula. And so what is the connection between this form and that form? Well, you should think of this as u equals f of t, right? And then you say dv equals g prime of t dt. Then standard calculus manipulations say that du should be f prime of t dt and v should be g of t. And then you plug in and it gives you the right-hand side. Now, how do you go from here to there formally? We haven't discussed that, but this is basically using the formalism of differential forms. What you do here really is that what you're doing is the following. You say, let me call u this differential zero form. You take what is called exterior derivative of it to get du. It turns out that a zero form, when differentiated, becomes a one form. So this is how you differentiate it. And in a one form, you sort of look at an antiderivative. And that gives you the situation. If you take the sequel class, you're going to learn all about this formalism. So here, u, the differential zero forms, du, dv are differential one forms. In multivariable calculus, you have 2 forms, 3 forms, and so on. Keeps going on like this. Okay, let's prove it. I would like to use the fundamental theorem, of course. Oh, maybe I should have stated also that everything here makes sense. So let f, g be here, and f and g are differentiable with their derivatives Riemann integrable. Then this guy is Riemann integrable, this product. And so is this guy, and this formula holds. Okay, I'm not going to write it. Everything here makes sense too. That's part of the statement. This is, by the way, not the most general integration by parts, but maybe in the next problem set you're going to see something about that. Because it turns out, okay, I'll mention something about it in a second. Let's first prove it. So what is the thing that I'm integrating here? It is this product function plus this product function. Right? So if I were to take this integral to the other side, I'm integrating some function, and I'm saying that this is the sort of nicer part of it. It's the sort of right-hand side. And so f and g are differentiable, and f prime and g prime are Riemann integrable. Then by the exercise, f g prime plus f prime g, as well as this, as well as that, are all Riemann integrable. They're all Riemann integrable. Okay. But of course, I also have that this function has an antiderivative. Because f times g prime gives me precisely this function. Antiderivative of this. So I have a Riemann integrable function here. Here. That's a Riemann integrable function, and I know at least one antiderivative of it. I can use these two functions then and the first fundamental theorem to get something. I'm going to be a little bit more explicit here. I can start with these two integrals. By the additivity property of Riemann integrals, the sum of the integrals is the integral of the sum. But then this has an antiderivative f times g, which means that I can apply the first fundamental theorem to write this, right, the integral of the derivative on the whole thing as the integral of the function on the boundary, this Balkan boundary correspondence. And so this is exactly what I want. And how did I come up with this function? How did I realize that I should be looking at this? Well, I just compiled all the functions in this formula that are being integrated. Okay? That's how I came up with this. Any questions about this? It's not very sophisticated, but seeing where to apply the fundamental theorem does become a problem, as you see. It becomes an art. You need to have some experience about that. Okay, so now let's switch over to the U substitution formula, at least one version of it. Okay, I'm going to say two versions. One of them is the one described in the textbook. The other one is more natural. There are many other change of variables formula, it turns out. There's a whole cottage industry I learned over the weekend with varying generality, all for Riemann integrals, and beyond too, possibly. But let's stick to this version. So I'm going to take another interval. Let's call it L to R. Again, it's closed and bounded. Now, the change of variables formula is kind of awkward. In which direction you're changing the variables, formally speaking, becomes complicated. But I want something like this. Okay? This is R, this is I, this is J. I want to have here an integrable function. And instead of integrating over J, I want to have a function here, a change of variables function that I'm going to denote by capital Phi. And instead of integrating f over this function, over this interval, I would like to integrate the composition over this interval. And for it to be more evocative, let's say that the variable of j is u and the variable of I is t. So I want something like this. Let's say that phi takes the endpoints of I to the endpoints of j. Okay, I have to write f of u du. And so I'm saying u equals something something, right? That's how you do u substitution. I want this to be equal to the integral of the composition where now your variable is in I. So it goes from lambda to rho dt. And so what you're saying is, it's kind of awkward, but for instance, in single variable calculus, you have some function phi, and you call u that function, and then you say du equals phi prime dt, right? And so you sort of like get rid of this as well. But of course, there's a problem here, because if you call u phi of t, or rather phi of t u, so that this expression becomes f of u, you want some factor here so that whatever is remaining compiles into du, which means that this doesn't quite work. But if you were to add this factor, this distortion factor, phi prime over here, now it works. This is the case in single variable calculus. This is the case in multivariable calculus, whatever. Whenever, for instance, you switch over to the polar coordinates, right? So x equals r cosine of theta and y equals r sine theta. You have dx dy turns into r dr d theta. You have that r factor. It is related to this, even though it is a multivariable. Any questions about this? So this I would like to formalize. Probably we're not going to have time to prove it, but at the very least tried it. Let f be Riemann integrable on J phi be differentiable on I differentiable with derivative integrable, so that this right hand side with this factor makes sense. And let's say that phi of I equals J. Then, for any alpha and beta in I, I'm going to write a statement for signed integrals. So here I want to have f of u du, and here I want to have f composed with phi of t times phi prime of t dt. So here, the integral varies from alpha to beta. Here, I need to change the endpoints as well. Alpha is going to turn into phi of alpha, right? So if here's alpha and here's beta, if I'm integrating from alpha to beta, I should be integrating from phi of alpha to phi of beta. And so that's how you write it. And of course, this integral makes sense. Okay, this is one version of the change of variables formula. Tomorrow, I would like to prove at least this version and discuss a little bit this improper integrals. And that's, I think, a good place to stop for today. Thank you. Okay, let's start. Good morning. So today is our last official class for integration. Probably I'm going to be taking the first class of next week to discuss some interesting stuff. And then we're going to start talking about series. We're going to have a sequence of real numbers, and we're going to figure out a bunch of different ways to evaluate expressions of the following form. Infinite sums, So this is sort of like the discrete analog of one of these improper integrals. We're going to see this, and in fact, so this we're going to call a series. And in fact, on Monday, I would like to discuss something called weak derivatives. It's a notion of differentiation that is applicable even when the function is not differentiable in the sense that we discussed. It's going to be quite interesting. And I would like to discuss a theory of discrete calculus. Calculus that doesn't involve any type of limits, that applies to sequences of real numbers, let's say. And then we're going to switch over to understanding expressions of this form, figuring out when this makes sense, and so on. But before that, we need to cover two things. First is the so-called change of variables formula. I had mentioned it yesterday, but I would like to state it more properly this time again, and at least give two versions of it. And then I would like to say a couple words about improper integrals, this unbounded integrals. I decided I'm not going to spend too much time on the formalism behind it, but I just would like to say a couple words about it at the very least. So here's the situation, okay? Let me draw a picture. So I have one function f, lowercase f, defined on this interval. So this is R. Somewhere here is my closed and bounded interval J. Okay, this is my J. Its variables I'm going to call U. Okay, and it's from L to R. And I have a function defined on it. Lowercase f takes real values. Okay, send U to f of U. But then I have yet another interval that is before, I would like to imagine, before J. And I have a function, capital Phi, that goes from I to J. Okay, I to J. So the image of the interval I under the map Phi is J. Okay, this is another copy of R. I have now a red interval, I. It's from lambda to rho. Its variables I'm going to call T. And Phi takes the red interval to the blue interval. And I would like to be able to say something like the following. Instead of integrating f, assuming that it is integrable, over the blue interval, I would like to be able to integrate this composition function. Right, so the composition function is f composed with phi. I would like to integrate this function over the red interval. And change of variables basically says when you can do this, but there's a cost of doing this change, okay? The cost is related to the derivative of this guy. And we're going to see in a second how it shows up, even in the proof. I'm going to say two versions. One of them is for directed intervals, integrals, or rather signed integrals. And the other one is for unsigned integrals. And the assumptions are somewhat orthogonal. We're going to discuss that. So the first statement is the following. This is the statement given in the textbook. If f is continuous and phi is differentiable with the derivative Riemann integrable, then I have the change of variables formula. If f is C0, phi is differentiable, and phi prime, which is again a function from I to R, itself is Riemann integrable, then for any alpha and beta in I, in the red interval, I have the following. the signed integral from phi of alpha to phi of beta of f of u du equals the signed integral from alpha to beta of f composed with phi of t times, you see this is that cost that I mentioned, times the derivative of phi. That's the first formula. Now this shows up insofar as the derivative is not equal to 1, of course. Because somehow what this does, this change of variable does, is possibly that it perhaps expands or shrinks some of the pixels. And so that has an effect, okay? In the proof too, we're going to see that immediately. Okay. Now, in practice, it kind of works the other way around, because in practice, you start with something like this, but they don't tell you that, oh, I'm composing, so inside f, the function that you're trying to integrate, there's some other function, and its derivative is on the next, to the next of it. It's part of your job to do this u substitution, to realize that whatever is inside f, its derivative is next to it as well. And then you say capital phi of t is u, and du is equal to this, and that's how you get to switch over to this, okay? So in practice, there's a second part. Okay, I'll write it here, doesn't matter. In practice, one puts u equals phi of t and realizes that there's a remainder. And then du becomes equal to this guy. So in single variable calculus, or in the first class that you ever took about these kind of things, the main challenge was to realize that, oh, next to this function that you're trying to integrate, you do indeed have an expression of this form. You call whatever is inside f u, and then you have to realize, or you have to figure out that du is indeed of this form. In abstract, that's not really a major issue. Okay. I'm reiterating this because in the abstract, so the directions sort of get complicated a little bit. Any questions about this statement? The second version is for unsigned integrals. Now I'm going to assume less about about the function, but I'm going to assume more about the change of variables. The second part, let me write it here. If f is Riemann integrable and phi is a C1 diffeomorphism, so it's a C1 function, continuously differentiable from I to j, has an inverse, its inverse too is continuously differentiable. This is in a sense the most natural sort of context in which you would want to do a change of variables. And remember when I first defined this diff1 set, this is a set of all C1 diffeomorphisms from I to j, I said that this is the space of all u substitutions. It's, in a sense, more natural to think about this as opposed to the first case. If f is Riemann integrable and phi is a C1 diffeomorphism from I to j, then now I'm going to have a statement about unsigned integrals, but it's going to be sort of similar. The unsigned integral of f over j is equal to the unsigned integral of f composed with phi times. Now I need to be careful. Instead of just saying phi prime, I need to actually put phi prime in absolute value. Because maybe the direction changes, but for the unsigned integral, that shouldn't matter. Okay? So typically in single variable calculus, they state this, and then they don't really worry about this one. But then when you switch over to multivariable calculus, you want to have a change of variables formula. And then there, the formula requires that you have this absolute value. And then people say a couple words about why it should be there and stuff like that. But even in single variable calculus, if you're only considering unsigned integrals, you should be putting the absolute values there. And it's going to show up in the proof too, why this should be like this. Of course, in multivariable calculus, a diffeomorphism from a box to another box, let's say, is going to be a function, all of whose partial derivatives exist. And somehow this derivative, instead of this derivative, or the absolute value of the derivative, what you look at is the absolute value of the determinant of the matrix of partial derivatives, if you know what that means. Okay? Any questions about the statement of this? Okay? Let's prove item 1. Item 1 is rather straightforward compared to the second item, because we can prove immediately item 1 using fundamental theorems of calculus. For the second, it's slightly trickier, and I thought it would be, so the proof I came up with uses basically the definitions of upper and lower Darboux-sums and so on. Okay. Now, I should mention perhaps, if f is continuous and phi is differentiable, then phi is also continuous, which means that this composition function is continuous. In particular, it is Riemann integrable. This too is Riemann integrable by assumption, which means that this product, by this exercise that I gave you, is Riemann integrable. So everything makes sense here. And likewise, I can argue that everything here makes sense. Okay? That's not an issue. I'm not going to state it. So we're trying to prove the first item. Let's see. Okay. I know that f is continuous, lowercase f, because I'm assuming it. Then by the second fundamental theorem, I can look at this capital F function, one of these, and that's going to be a C1 function. For any gamma in, I guess, in J, consider f sub gamma, which goes from J to R, defined like this, right? So f sub gamma of x, this was this cocycle function, the integral from gamma to x of f. Okay. By the second fundamental theorem, we know that whenever the integrand is continuous, this cocycle function is going to be differentiable, and its derivative is going to be the lowercase f. The C1 differentiable, and f gamma prime is lowercase f. Okay. Okay, nice. Now I look at capital F, one of these capital F's, composed with this phi function. So then, capital F sub gamma composed with phi, this is the composition of two differentiable functions. We had shown that the composition of two differentiable functions is differentiable, which means that this is differentiable. And if I were to differentiate this, what do I get? This is, by the chain rule, the derivative of the guy to the left composed with the guy to the right times the derivative of the guy inside, right? But capital F prime is lowercase f, which means that I can write this as lowercase f composed with phi. Or maybe I should have used letter t for this. It's better. It doesn't matter, of course, these are dummy variables, but still. This is this times this guy. And furthermore, this guy is continuous. This is Riemann integrable. Their product is Riemann integrable. In other words, I have a Riemann integrable function, and I have an antiderivative of it. Thus, f composed with phi multiplied by phi prime, this guy, is a Riemann integrable function on I. And this guy is an antiderivative of it. For any gamma, this is an antiderivative. What is the next step? I use the second fundamental theorem, but I have the first fundamental theorem as well. How can I use this first fundamental theorem here? Any guesses? I'm slowing down because this is important. You see, this is how you use things like the fundamental theorem in abstract situations.
Put it into FTC1.
Say again? Yeah. Yes, but what does that tell me?
Well, it gives you the right-hand side of the equation that we want.
Okay, so you're saying that let me try to integrate this guy and do something with it using the first fundamental theorem.
Yeah, I mean, we know it's integrable.
Exactly. You can put this in.
We know how to work it.
And so by the first fundamental theorem, this is equal to any antiderivative of this function evaluated at beta minus evaluated at alpha. And so I'm going to use this guy. This is an antiderivative of this thing that I'm integrating, evaluated at beta minus evaluated at alpha. Okay? This is the first fundamental theorem. But then I can rewrite this using the cocycle identity if I wanted. Right, so these two cancel out, so this becomes this. By the cocycle identity, so but then what is this? By definition, this is the integral of f from phi of alpha to phi of beta, which is what I wanted. Questions about this? It is very important to understand how to use these fundamental theorems. And they're complicated statements because you have a couple different notions of antiderivatives or integral type things and derivatives and blah, blah, blah. And they are sort of interrelated somehow. And the two fundamental theorems really tell you how they are interrelated. And you see, it becomes very important. Even though this f sub gamma business it looks very bizarre, at least when I first learned about it, it was like, it took me a while to sort of come to terms with this expression here as a function of x. It's like a next step thing, I think. But you really need to be able to understand this function as a function of this x, and really sort of use it to compose with some other functions and so on. Questions? Comments? Yes?
Can you explain how you use the FTC2 again?
Fundamental theorem of calculus item number 2 is all about functions of this form. Now, because I'm assuming that the lowercase f is continuous, in particular it is Riemann integrable. In general, fundamental theorem of calculus 2 says that whenever this thing that you're trying to integrate is integrable, this makes sense. Okay? And it's a continuous function. But I want more. I want it to be differentiable. But part of fundamental theorem of calculus item 2 is that if the thing that you're trying to integrate is continuous, this guy is going to be better than continuous. So it's going to be differentiable. Once I'm assuming that lowercase f is continuous, uppercase f is going to be once differentiable at the very least. Then I can compose this guy with this and differentiate it to use the chain rule and stuff. Does this make sense? Okay, so in summary, you have this. Part of fundamental theorem of calculus 2 says that this is well defined. And another part of it says that this guy is in fact C1, once differentiable with the first derivative continuous, and its derivative is equal to this thing that you're integrating. Okay? So in a sense, you see, you get uppercase f by integrating lowercase f, and you can start with the uppercase f and differentiate it to get the lowercase f. So differentiation and integration is opposite operations. And so imagining this to be sort of like an integral, fundamental theorem of calculus governs how to differentiate the integral. First integrate, then differentiate. Fundamental theorem of calculus 1 says it the other way around. First differentiate, then integrate. Okay? Loosely speaking. Any other questions? Does this make sense, what I said? You're not happy? Oh, okay, okay. Yeah, yeah. Yeah, it is confusing, all this stuff. It is confusing. And you know, part of it could be my notation. I would highly recommend that you sort of write things down in your own notation and stuff. Okay, let's try to prove item 2. It's going to be more complicated this time. We're going to need to do some proofs. For instance, for item I, we had this sort of compositionality of two continuous functions, and that immediately gave us that this is continuous. In particular, it is Riemann integrable. But in this case, we actually don't have that. We haven't done anything about compositionality when it comes to Riemann integrability, right? So f is Riemann integrable, the other guy is differentiable. I don't know at this point, actually, that this is Riemann integrable. It is true, but that's something that needs to be proven. And this is also why integration is sort of like a different beast. So we started with, for instance, continuous functions. We said that the composition of continuous functions is continuous. Then we switched over to differentiable functions. We realized that the composition of differentiable functions is differentiable. And, you know, twice differentiable, 3 times differentiable, doesn't matter. But it turns out that the composition of integrable functions is not necessarily integrable. Okay? So, and this is sort of like a general issue with integrability. Integrability doesn't work well with sort of compositions of functions. And that's why, for instance, instead of saying I have a Riemann integrable function and my change of variables too is just Riemann integrable, you need to assume more. That's sort of like a typical thing in general. Okay, so the proof of item 2. So we need 2 steps for the proof of 2. First, we need to prove that this thing that is being integrated is integrable. And then we need to show the equality of the integrals. Step 1. This function is Riemann integrable. Step 2, the equality of integrals. Okay, let's first prove step 1. It's going to take a while, the proof of this, but it is useful, illuminating, and it's a nice proof. That's why I'm doing it. So proof of step 1. The way I prove this is that because I know by the exercise this function is integrable if this is integrable, right? Because I'm assuming that lowercase f is integrable, phi is differentiable. I don't quite know that this composition is integrable, but certainly I know that phi prime, which is continuous by the assumption, is integrable, which means that its absolute value too is integrable. So it suffices for me to prove that this composition is integrable. Then by the exercise, this is going to be integrable. So by the exercise from yesterday, it suffices to show that f composed with phi is Riemann integrable. Okay. So let me draw a picture. This is my I, this is my j, and here's the reals. That's the situation. Now I need to play with the partitions, right? I'm trying to show that f composed with phi is Riemann integrable. So I'm going to start with a partition of I. Let's say it's this guy. That's curly p. Then I'm going to push each of these pixels forward using capital phi. In other words, I can look at these cut points, look at their images under phi. Those images are going to cut the j interval. Okay? So this I'm going to call this guy. So let P be an interval partition of I. Perhaps I can be a little bit more explicit here. So that means that P is of the following form. Lambda to T1, T1 to T2, and so on, all the way up to T sub n minus 2 to T sub n minus 1, and then T sub n minus 1 to the right endpoint. That's my partition. And of course here I mean that lambda is equal to T0 and so on. Now, phi of curly p is going to be a pixel, is going to be a partition of j made up of, well, the images of these intervals. I know that the images of intervals under diffeomorphisms, in particular homeomorphisms, in fact, or continuous functions, are intervals. But in any event, this is going to be a partition, you see. So it's going to be like this. L to, let's say, U1 to U2, and so on, all the way up to U sub n minus 1 to R, where L is equal to U sub 0, and then U sub 1, and so on. Now, the problem is that I can't quite say at this stage that, for instance, U sub 1 is equal to phi of T sub 1. Because maybe phi changes the orientation. Think about, for instance, phi of x equals 1 minus x for the unit interval. But in any event, I know that these cut points are going to have the same number. In other words, I'm going to have exactly the same number of pixels in the push forward. That's sort of like the more formal name for this. The push forward partition and the original partition. They're going to have the same number of pixels. Where ui is equal to phi of ti for any I, XOR, so for any I, XOR ui is equal to phi of, so either T1 is going to be sent to U1, or it's going to be sent to this guy. In other words, T n minus I. Maybe I should write it like this. Okay. It's cumbersome to write this down, but all I'm trying to say is this, okay? If your cut points are this way, phi either preserves the orientation in the same order, or it has to exactly complete the flip. Okay? That's what I'm trying to say here. So this is the orientation preserving case. This is the case where phi prime is always positive. Or this is the other case where phi prime is always negative. So orientation preserving versus orientation reversing case. And this is the case of phi orientation reversing. Okay, now to each of these pixels, I'm going to apply the mean value theorem to get points, sample points, where the rise over run are given by the derivative, right? Is this? You see, for the item 1, we just applied the fundamental theorem, but for item 2, because of this pesky absolute value, you end up needing to open up the definitions and work a little bit more. This is probably going to be the most involved proof we're going to be doing in this class. Apart from perhaps L'Hopital, actually. L'Hopital was complicated also. It's not as deep compared to this, though. OK, so applying, so let me also call one of these pixels p sub I. So this is going to be p sub 1, p sub 2, and so on. And the images are going to be q sub 1, q sub 2, depending on which I'm looking at. So call p sub I minus 1, t sub I. Then, by the mean value theorem, for any I, there is an S of p sub I inside p sub I, such that this happens. We had applied this idea a couple times already, even in the proof of the first fundamental theorem, for instance. We had a differentiable function, and we sort of applied the mean value theorem to each pixel of a given partition. Now, the point here is that I would like to interpret this more geometrically. The denominator here is really the length of the pixel p sub I. And the numerator is the length of the image of the pixel, p sub I, up to and minus possibly, because I don't know if phi preserves the order. And so, but if I were to take the absolute values, this would be correct no matter what, so that I would have the following. This is the length of the image pixel and this is the length of the original pixel. S of p sub I in absolute value. And so you see, this is a geometric interpretation of the derivative. In a sense, this is the weaker interpretation of the derivative of a function. What this is really telling you is that phi prime is the, distortion coefficient. You have one pixel, you apply some function phi to it, turns into some other pixel in some other place. The lengths are distorted by exactly this value, the derivative. Okay, so how do I want to write this? Well, let me leave it like this for now. But of course, phi is a C1 diffeomorphism. Its derivative, therefore, is a continuous function. It's always positive or it's always negative. Okay, because the derivative of a continuous of a differentiable function of a diffeomorphism cannot be 0. So it's always going to be positive or always going to be negative. In any event, if I were to look at the absolute value of the derivative, this is bounded by some positive number from below and from above. So since phi is a C1 diffeo, phi prime is never 0 and is continuous on a closed and bounded interval. We know by the maximum principle it has to attain its minimum and maximum. And so let's write it like this. Min of phi prime in absolute value is a positive number. Okay, that's a trick. So that this ratio is bounded like this. This is bounded from above by the max of phi prime in absolute value and by the min from below of the same function. So this max of phi prime in absolute value is the largest distortion, and this is the least distortion phi causes. Okay? So this is the largest distortion. Largest length distortion phi causes. And this is the least distortion phi causes. If these are both 1, in other words, the ratio of the lengths were 1, that would be the best case in a sense. No distortion, which is called the isometric case, isometric case. And so we said that this is a positive number. Okay, this proof took longer than I thought. Any questions so far? We're not done yet, but we have all the ingredients. The point here is that I have a partition of I, okay? And in fact, for that partition, I have a sampling function also. So I have a Riemann sum. Riemann sum for this composition function. Now I need to compare that Riemann sum to some Riemann sum for lowercase f. And I'm going to use this this inequality here. So let me continue from here. Probably we're going to do step 2 next Monday. So now I'm looking at, this is the function I'm trying to integrate. Oh, sorry. Let me just look at the Riemann sum first. Should I look at the Riemann sum? Well, I guess I can just look at the upper and lower Darboux sums. Recall that curly P was an arbitrary partition of I, and f composed with phi was the function I'm trying to show is integrable. In other words, if I can bound this guy, this difference, by some epsilon, by choosing a nice partition, I would be done. And so now, writing this out, this is like this. Just writing the definition. F of f composed with phi restricted to p. This multiplied by the length of the pixel p. But then this is nothing but instead of thinking about the restriction of the composition to the pixel p, I can instead think about f restricted to phi of p. It's a silly thing to say, but it is true nonetheless. And instead of L of p, you see, I can write it the other way around. So that's what I'm going to need to do. Which one do I want? Yeah, so I can send this here and this there, which tells me that L of pi is bounded from above by L of phi of pi divided by this min. It's a positive number, which means I can do that. And so if I were to replace this L of p by this, that would possibly increase. So min of phi prime in absolute value. Do I have time? Yes, I have time. OK. So you see, we're almost done. The point here is that this is a number, so I can take it outside the summation here. 1 over min of phi prime in absolute value times summation over all pixels, sup of f restricted to the image pixel minus inf of f restricted to the image pixel times the length of that image pixel. But this is nothing but the upper minus lower for f relative to the image partition. So we were able to show that for any partition P of I, the gap between upper and lower is bounded from above by this expression. I can do the same thing the other way around, of course. If I were to start with some partition Q of J, so if I were to call this Q, P would be the pre-image partition. Likewise this. In any event, I know that for any epsilon, there is a Q such that this is bounded by epsilon, which means that looking at the pre-image partition, this I can bound also. And that proves that f composed with phi is integrable. So that's the end of step 1. We're going to have to do step 2 next Monday. Thank you. We're done with this stuff for midterm. Tomorrow we're going to have review, so come with your questions and stuff.